derivation and boil it down to what you need to do. What? Did you say something?
I was having a conversation with myself and
Oh.
yelled at me.
Right. Oops. I left out the other term there. I'm sorry. I had that whole sum of terms, and the next term out looked like this. Integral, there's a prefactor, but it's integral j r hat dot r prime dv prime. I'm going to integrate by parts there as well. So there's some prefactors to this. So what I can just write is that the vector potential is proportional to that. This would be the second term in the series. So the first term was a dipole oscillator, right? The second term has got something else going on there, right? We're going to use that. We're going to use two tricks. One vector trick is this, and you might ask why, and the answer is because it ends up splitting the integrals that you have to do into two physical terms, each of which can be identified as having a particular behavior. So it's certainly not odd that you look at this and you say, oh, do the integral. That's not J at all. Just do the integral, and that's true. But we want to split it apart into terms that that we can identify as having a particular physical origin. And we're going to use this trick. I'm going to prime them just because this. Minus two terms, okay? But then you look at it and you say, but wait, that's not over there. I've just got r dot r prime. But I've got r dot r prime j. That's one of the terms over there, right? So r dot r prime j is equal to this plus this. And I can write this now as 1/2 integral r hat dot r prime j minus r dot j r prime plus 1/2 the integral, whoops, r prime cross j cross r hat. Okay. The first term, you actually might recognize this. This is actually, looks like the electric quadrupole term we did when we did quadrupole moments. Right? This term doesn't. This term actually looks more like a current circulating something. Right? This term actually is the magnetic dipole moment of the current distribution. So this one is electric quadrupole. And this one is a magnetic dipole. The magnetic dipole moment is actually defined like this, just to remind you. M is 1/2C integral it's that, which is the same as that, aside from a factor of c. Okay? So what that means then is that this term, so now I've got two possible terms here, magnetic dipole, electric quadrupole. They actually both drop off at the same, with the same R dependence, right? But this one we can just say, if I have only a current circulating, I'm not moving charge around the problem. The charge is constant, right? I just have current going around, right? Then I have my magnetic dipole, and the vector field, vector potential for the magnetic dipole is equal to, I don't have to worry about the proportion here because I'm copying this from somewhere, 1 over c squared r, the distance, r hat cross dm dt. And I seem to have dropped an e to the I, k, r, oh no, I haven't. I'm okay. No. I suspect that I've dropped a factor of 4 pi over c here somewhere as well. But that's the bottom, the basic idea. The vector potential drops then is 1 over r squared. I think I just dropped the e to the ik on it. I'm going to leave it like that. See if I correct it. All right, I will check that to make sure. From which then the magnetic field for that magnetic dipole term, this one here, then just looks like this. V is 1 over c squared. I think I got the right. R hat cross R hat cross acceleration rate of change, second derivative of the magnetic dipole moment with respect to time. Yes.
That's still evaluated at GDM?
Yeah, what I mean by the brackets
Yeah.
is always evaluated at that retarded time, however long it takes to get there. Prior time. And for a harmonic dipole, the pointing vector is proportional to omega squared, omega to the 4th, once again. The electric field can be deduced by just taking the curl of the magnetic field. And then this next term here, again, we look at the charge distribution, but sorry, not the charge distribution, the current distribution, and we calculate the equivalent of the quadrupole moment. That, you know, we had charge distribution and we calculated the quadrupole moment before. Now we have current distribution, but the calculation is the same. So the next term that we would calculate would be due to the electric quadrupole, right? So then it gets complicated. These three terms are the dominant terms for the radiation from oscillating atoms and nuclei, basically, right? So being able, given the spin of a system or a transition between two states, quantum mechanical transition between two states, we can write down the current distribution or the dipole moment, the magnetic dipole moment, and calculate the radiation from that atom. So on this scale, with the assumptions that we made about the distance from the observation point and the size of the system with respect to the wavelength, what I've done here applies to a classical analysis of the radiation of atoms. Okay? And I think I'm probably going to finish there for today. I still have yet in this course, I'm going to spend one lecture on waveguides, because you can't get out of an electromagnetics course without knowing a little bit about waveguides. And I actually am forced to say, if you want to learn a lot about waveguides, you might want to take fields and waves in the electrical engineering department. But you'll find the first half of fields and waves to be a repeat of most of what we've done here. But then they just go straight into waveguides after that. And antennas and waveguides. And then I'm going to do one lecture on diffraction. Okay, that's it.